What exactly does research in mathematics at the PhD level look like? I don't have the best answer for this because it kind of comes about from a problem that maybe a potential advisor would come up with, but there's nothing out there that says that you can't also come up with a problem. The issue is whether or not you can pitch that problem to a potential advisor and you think you can make reasonable work on it. It's not, I don't think, as rigid as you might expect. I mean, it depends on the institution, obviously, and what the advisor that you want to work with wants to do. But I decided to show you at least 3 problems that are potential areas of research and tell you just exactly where these problems came from. Okay, so let's start with the first one. Hopefully my pen works. It does. Okay, so this problem I asked from my analysis instructor about a year ago. I wanted him to, I was wanting to do research with him. He's a pretty big name in analysis, and he works on hard problems, and he's known for tackling really hard problems. So I asked him for one just to see if I could sink my teeth into it. And he gave me the problem, and I wrote it down on a sheet of paper, and I've kept the sheet of paper on my shelf for the past year now. And unfortunately, I haven't really gotten to work on it much because, you have classes and distractions that prevent you from doing research, which is unfortunate. But I have it written down here. I wrote it down, and it's a tough problem. Surprise, surprise. But here's the statement. So here's the paper. What exactly does it say? So you look at a continuous function phi. It's non-negative, and it's infinitely differentiable. So it's a function of Rn. So it takes on a vector in Rn, and it returns a real number. And the function's infinitely differentiable, and it never becomes negative. Pretty simple to think about. And then you have some number s bigger than 1, and he tells me that it's roughly equal to n divided by 2. So half of the dimension of the space that you're in. All right. Now this is the definition of a convolution. So we take phi star g t naught. So g is some function here, and it's equal to this convolution. And unfortunately, it's a little bit hard to read here because originally we were integrating with respect to s, and I got confused, and I said, how are we integrating with respect to s when s is roughly a constant up here? And then he said, no, this s is different from this s. So to correct the notation, I replaced it with t, I believe. So I have t naught minus t inside. I have a t inside here and a t inside, or a t right here, dt. All right, so what does the next statement say? So phi star x divided by x to the s is equal to u. So u is a convolution, and I'm convoluting it. I'm not sure what the word is. I don't really know much about convolutions, to be honest with you. They never really showed up in a course that I took. I think it's more of an applied math thing, but I don't know. But you have phi star this vector. So you have x here, and then you normalize it. Kind of normalize it. You raise it to the s power at the bottom. So you have this function. And what's the problem say? The problem says I want to find a constant c that's dependent only upon n and s. Although s depends on n, so it's really just dependent upon s, I guess. So find a constant c such that the following holds. The maximum value of the absolute value of u over the whole space is bounded above by c times the maximum value of that same function over the support of phi. So when I first saw this, I was a bit confused by this statement because, Like, wouldn't this always be greater than or equal to this? And that's true. That is true. But the game here is that here you're looking at the maximum value over all of the whole space, whereas over here you're only looking at it on the support of phi. So this max value can only get smaller, and that's where the constant c comes into play. You want to choose some sort of c such that this value exceeds that value. So the guy that gave me this problem says he's been thinking about it on and off for about 8 years now. And this guy that gave it to me, he's notoriously smart. He's the one that wrote the qualifying exam that I showed on my channel not too long ago. And he says he's not really sure what to do with it. He's been working on it for 8 years, and he says it needs a new pair of eyes. So when he told me about it, I was like, yeah, I'll look at it. And then I looked at it and kind of tried to just make something up, just write some stuff down. I really didn't give this an honest attempt. It's just been sitting on my shelf, and I think about it from time to time. I believe I wrote some stuff on the other side. What do we know? So I just wrote some things down that I knew. That's usually my approach a lot of the times. I just write down the things that I know, and hopefully something will come up that I can make some sort of claim with. I don't know if I'm really going to try this problem. If he can't do it in 8 years, then I'm probably not going to be able to do it and get a PhD in 2 years. Because I don't really want to be in my program for more than 2 more years. I want to get this PhD done and then get a job and start, living. Quit being a grad student. But this is an example of an open problem that you can do research in. If anyone has any suggestions about how to approach this problem, I am all ears. Definitely. So that's one problem. Well, let's start with a second one. So what's another problem I've been looking at? So a guy down the hall, I take a class with him. He does a lot of problems in geometry. And he proposed an interesting problem in class that he didn't know the answer to. I don't know if this is an open problem, but I couldn't really find anything on the internet about it. And I've been working on this problem, and I think I've made some progress on it, which I'm kind of excited about. I'm going to meet with him tomorrow and show him something I came up with. But he gave me a sub-problem, I guess you could say. He asked me a question about my method. Like, can you construct a shape that does this? And I believe I can. And I worked on it yesterday, and so I'm going to show it to him tomorrow. Anyway, what's the problem? So it's called the existence of the universal body. Existence of the universal body. So what does this say? The question is this: does there exist a convex body, which I call U, in R3? Does there exist a convex body U in R3 such that, how do I write this? For any convex body K in R2, there exists a plane in R3 where, so I want to take K and intersect it with pi, and that's going to be isomorphic to, U, sorry. U intersect pi, and that's going to be isomorphic to K. Question mark. All right, so what does this problem say? We are interested in a convex body that exists in three-dimensional space. So think of like a cube or a sphere or an ellipsoid, any shape in 3D space, but it has to be convex. So what does convex mean? It means that if you take any 2 points inside the shape and connect it with a line segment, then the line segment is completely contained within the body. So for example, a circle is a convex body because if I take 2 points inside the circle and connect them, the line segment's still inside the circle. But if I draw like a noodle, like this is not a convex body because I can choose this point here and this point here, connect them with a line segment, and the line segment exits the body at some point. So this is convex, this is not. So does there exist a body, convex body U, such that for any, I forgot something, R2. Such that for any convex body in the plane, and this is true for any convex body in the plane, I can find a plane in three-dimensional space such that when I slice it into my U set, I can get a shape that's isomorphic to K. So for example, let's say that this weird object, which I'm going to call U, I take a plane. Well, okay, the question here is there a cross-section that gives me a square? Is there a cross-section that gives me a circle? Is there a cross-section that gives me a pentagon? Is there a cross-section that gives me a body of revolution? Like with the sine curve? Question mark. And the idea is that given any one of these shapes, so these are my K's, I can find a plane that passes through U like this. So here's my shape. So this is pi and this is U. So that this cross section here is my pi intersect U. And this shape here is supposed to be isomorphic or homeomorphic or whatever you want to call it, congruent, whatever the geometry word is, to K. I don't really care too much about the size, just that I can get the shape. So he proposed this question in class. The class is called Problems in Uniqueness, but I call it convex geometry because that's really all it's about. So he proposed this problem to us, and when he wrote it up on the board, he goes, "Does such a body exist?" Which he calls the universal convex body. And when he said that, I was like, no way. There's no way this thing exists because look at how many convex shapes there are. I mean, it's so complicated. And he goes, I don't know. There might be a set. It depends on how you have to think about it. So he doesn't really know. So I was working on this problem over a weekend, and I came up with something interesting. I didn't solve it, but I came up with an interesting approach. And I showed it to him, and I don't know, I don't want to use the word that he was impressed, but I will say that he was intrigued, and it made him ask some follow-up questions. So then he proposed me a new problem that's supposed to aid in this construction, and I believe I solved his problem, and I'm going to show it to him tomorrow. So that's kind of exciting. I also think this problem's interesting. You know, when I look at this one, when I look at this problem, I just get scared and I want to go home and cry. But with this problem, this is like a puzzle almost. And I appreciate the puzzly math problems more than the ones that bring about the worst in people. We'll put it that way. So that's one area. And then for the third problem, I'm going to show you a problem that I came up with. And I've been workshopping it and trying to see if I can pitch it to someone. I pitched it to one guy, but he says he's not really an expert in this field of study. So, and he also told me that he's basically retired and he doesn't want to start a project with a student. I was a bit upset when he told me that, but I mean, what are you going to do? So what does the problem say? Where I got my thesis, how do I explain this in a very concise manner? Where I got my thesis, I did research that involved Cantor sets. So if you remember Cantor sets, you have an interval, and then you can remove an interval on the inside. So this is the middle thirds Cantor set. And then during each stage of the construction, you remove the middle interval every time. And you do that until, you do that ad infinitum. And so we considered sets like this. So if this is C0, C1, C2, C3, then the Cantor set is going to be the intersection of all those C sets. Cantor set. I'm not explaining this very well. I'm assuming that you have some knowledge about the Cantor set, because I want to explain this in 5 minutes. So what do I want to do? So we consider the deleted digits construction of these Cantor sets, and then we want to translate this Cantor set in such a way that we can get a Hausdorff dimension of a certain value. So what exactly do I mean by that? So how am I going to explain this? Okay, we'll do it this way. So again, my research was about this, so I remember. It is kind of amazing just how much you remember of your own research when you haven't looked at it in a long time. Because when you work on a problem every single day for like 2 years, it becomes incorporated in you. So these digits, no, I don't want to use N, are in some digit set. And by the N here, I mean I'm using an n-ary system. So if it's 10 here, it's decimal, it's 3, it's ternary, so on and so forth. And I define CK to be the set of all ternary numbers, or n-ary numbers, I should say, such that DI is in some restricted digit set for all I less than or equal to k. So n is some natural number bigger than 1. D is a digit set. And then D star is some restricted digit set. In the case of the middle thirds Cantor set, n is equal to 3, D is 0, 1, and 2, and the restricted digit set is 0 and 2. And for this statement here is the first k digits have to be a 0 or a 2, and then everything else can be whatever, doesn't matter. And then the Cantor set is simply the intersection of those CKs. All right, so new definition. X is in the Cantor set. I screwed that up. You'll find that when you're studying mathematics, if you're like me, you make a lot of mistakes, and then you have to go back over and correct it. So, god dang it. All right, how about we stop being an idiot here and actually write the thing that I want to write. There. So C plus T is simply the Cantor set translated by T for some fixed T. Okay, so what is the proposition? The proposition that I'm interested in, now this has already been proved, but it's related to what I want to show. There. So what does this say? It says that for any epsilon between 0 and 1, I can find a t that I can translate my Cantor set by, such that the Hausdorff dimension, or fractal dimension, or in this case Minkowski dimension, it turned out to be the same. The Hausdorff dimension of the Cantor set intersected with its translate, so it's a subset, is equal to epsilon times the Hausdorff dimension of C. So the Hausdorff dimension or fractal dimension of your Cantor set is some number. And the idea is that you only take a fraction of that number. And so given a fraction of that number, can you find a subset? Essentially, can you find a subset that has that fractal dimension? And the proposition here under this deleted digit set construction says yes, you can. And this was in a paper that was written by my thesis advisor about 10 years before I came around. Now, so the idea here is that I wanted to take that same idea and extend it to less well-behaved Cantor sets. So here's my question. And without going into too great detail, I'll just write, can you do the same for non-self-similar Cantor sets? I'll put in parentheses fat Cantor sets. But it doesn't have to necessarily be Cantor sets. It could be a bunch of things, you know. They could still be self-similar, so that's a less restrictive question that you could ask. But instead of removing like the middle third, like perhaps you remove the middle quarter or the middle half, if you want to make it thick, or skinny, I should say. Then can you do the same thing? Well, under the method that was used to prove this involves choosing these digits in these sets in a very particular way, and then translating them, and then constructing the T based on those digits that were picked. But the problem with these Cantor sets is that they're not, what's the word? Choosing digits is like impossible, because how do you, like, for example, like, if this is my Cantor set, and it's ternary, so if it's in a ternary system, it's easy for me to remove that middle interval. But what if you want to remove that piece in the middle? How do you find these endpoints using digits? It's a harder question to answer. And my proposed solution to this was to essentially construct some sort of bijective continuous map between 0, 1 and 0, 1, and then pass the Cantor set through this bijective map to get these quote-unquote I shouldn't say fat Cantor sets, because they're still self-similar if you do it this way. Fat Cantor sets are not self-similar. But if you want to do like middle quarter Cantor sets, I can find a one-to-one map between the two. One-to-one continuous bijection. In fact, there's a lot of them. And the question here was, what conditions do I need to impose on that set, or excuse me, on that function, such that it retains some sort of nice property about my Hausdorff dimension? Does this function exist? I have zero idea. I haven't really got to play with it much beyond that. But I pitched it to some people, or I pitched it to one guy. Actually, no, I'm lying. I pitched it to my thesis advisor not too long ago, and he says that it's an interesting idea, but you need to play with it more. And I pitched it to the second guy, and he said he wasn't really an expert in this and couldn't really help me. But I might pitch it to a third guy and just see what he says, but I want to work on it some more before I decide if it's worth pursuing, because at the end of the day, I really want to get my PhD, and it would be kind of cool to come up with your own problem and solve it. But, you know, if there's another problem that I'm making reasonable progress with, then I'll do that one instead. And I kind of like the universal convex body problem. I also feel geometry is the road less traveled. Perhaps. I don't really hear too much about geometry, so it's interesting to work on stuff like this. Anyway, that's a look at PhD level, a very, how do you say? In 25 minutes, this is how I would describe some research problems to people without going into too great a detail and without writing anything down. That causes that causes problems. So anyway, let me know what you think. Let me know if you have any suggestions or if you have any comments about doing research yourself, how this compares to doing research in other science fields. I'm interested in hearing what you have to say and just hearing from you guys. Anyway, thank you for watching.